Welcome to Cambridge IGCSE Physics, Lesson 20.1, Good and Bad Thermal Conductors. Today we explore how different materials conduct heat energy, examining the properties that make some materials excellent thermal conductors while others act as thermal insulators. This core content lesson builds essential understanding for your Cambridge IGCSE Physics examination. We'll investigate experimental methods to identify good and bad thermal conductors, compare material properties, and understand the practical applications of thermal conduction in everyday technology. Let's begin our scientific exploration of heat transfer through materials. Let's examine our learning objectives for today. By the end of this lesson, you will be able to, first, describe experiments to demonstrate good thermal conductors. This means you'll understand how to design and explain investigations that show which materials allow heat energy to transfer quickly through them. Second, describe experiments to demonstrate thermal insulators. You'll learn to identify and test materials that resist heat transfer, keeping thermal energy from moving through them easily. Third, compare materials based on thermal properties. This involves analyzing experimental results to rank materials from best to worst thermal conductors. These objectives align with Cambridge IGCSE Physics core content requirements and prepare you for examination questions on thermal conduction. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, thermal conductor, which means a material that allows heat energy to transfer through it easily. Examples include metals like copper and aluminum. Second, thermal insulator, which means a material that resists heat energy transfer, preventing thermal energy from moving through it quickly. Examples include wood, plastic, and air. Third, good conductor, which means a material with high thermal conductivity, allowing rapid heat transfer. Metals are typically good thermal conductors. Understanding these terms precisely is crucial for examination success. Remember to use SSI units, which stands for International System of Units, in all calculations and measurements. Let's explore our first core concept, thermal conduction fundamentals. The fundamental principle states that heat energy transfers through materials by conduction when there is direct contact between particles. This means thermal energy moves from hot regions to cold regions through the material itself. The definition is, thermal conduction occurs when kinetic energy transfers between particles in direct contact. Particles with high kinetic energy vibrate more rapidly and transfer energy to neighboring particles with lower kinetic energy. Key factors affecting conduction include material type affects conduction rate, with metals conducting better than non-metals. Temperature difference drives heat transfer, with larger differences causing faster transfer. And particle arrangement determines conductivity, with closely packed particles enabling better energy transfer. The diagram illustrates heat transfer through a metal rod, showing energetic red particles at the hot end transferring energy to less energetic blue particles at the cold end. Now we examine the experimental method for testing thermal conductors. This follows Cambridge IGCSE standards. The standard procedure compares heat transfer rates through different materials under identical conditions. The apparatus needed includes metal rods of different materials like copper, steel, and aluminum, small pieces of wax to attach to the rods, a controlled heat source such as a Bunsen burner, and thermometers to measure temperature changes. The method consists of these steps. First, attach wax pieces at equal intervals along each rod. Second, heat one end of all rods simultaneously using the same heat source. Third, observe which wax pieces melt first and record the order. Fourth, measure temperature changes at fixed time intervals. Safety is paramount. The hazards include burns from hot materials and eye damage from bright flames. Therefore, you must handle hot materials with tongs, wear safety goggles, and ensure adequate ventilation. The variables are: independent variable is material type, dependent variable is temperature change rate, and controlled variables include rod dimensions and heating time. Let's work through our first example. The problem states, 3 identical rods made of copper, steel, and wood are heated at one end, and wax pieces melt after 2, 5, and 15 minutes respectively. We are given copper rod causes wax to melt after 2 minutes, steel rod after 5 minutes, and wood rod after 15 minutes. We need to find the ranking of materials from best to worst thermal conductor. Step 1. Identify the pattern. We recognize that shorter melting time indicates better thermal conduction because heat energy reaches the wax faster. Step 2. Analyze the data. Copper shows the fastest heat transfer at 2 minutes, steel is intermediate at 5 minutes, and wood is slowest at 15 minutes. Step 3. Rank the materials. From best to worst, thermal conductor, copper, then steel, then wood. Step 4. Draw conclusions. This demonstrates that metals conduct heat better than non-metals, which is a fundamental principle in thermal physics. Example 2 applies thermal conduction analysis to temperature measurements. The problem is, temperature is measured at different distances along a copper rod after heating one end for a fixed time. The data shows temperature readings at various positions from the heat source. Now we analyze systematically. First, plot temperature versus distance graph. The red line shows copper data, demonstrating gradual temperature decrease with distance. Second, identify the temperature gradient pattern. Copper shows a steady, moderate decline in temperature, indicating good heat distribution throughout the material. Third, calculate the rate of temperature decrease. For copper, temperature drops approximately 7 degrees Celsius per centimeter. Fourth, compare with insulator behavior. The blue line shows wood data with rapid temperature drop near the heat source and minimal heat transfer to distant points. The graph clearly demonstrates that copper distributes heat energy more evenly than wood, confirming copper's superior thermal conductivity. Mathematical skills are crucial in thermal physics analysis. Let's examine 3 key skills for Cambridge IGCSE physics. First, temperature gradient calculation. The formula is gradient equals delta T divided by delta X, where delta T represents temperature change measured in degrees Celsius or Kelvin, and delta X represents distance change measured in centimeters or meters. The units are degrees Celsius per centimeter or Kelvin per meter. A steeper gradient indicates poorer thermal conduction. Second, rate calculations for heat transfer. The rate equals energy transferred divided by time taken, with units of joules per second, which equals watts. This quantifies how quickly thermal energy moves through materials. Third, percentage comparison for thermal efficiency. Efficiency equals useful energy output divided by total energy input multiplied by 100%. This helps compare different materials' effectiveness as thermal conductors or insulators. These mathematical tools enable quantitative analysis of experimental results. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, list 3 good thermal conductors and 3 thermal insulators. Think about materials you encounter daily and their thermal properties. Consider metals versus non-metals. Question 2 is intermediate level. It states, describe an experiment to compare thermal conductivity of different materials. This requires you to apply the experimental methods we've learned, including apparatus, procedure, variables, and safety considerations. Question 3 is advanced level. The question is, explain why metals are better thermal conductors than non-metals. This tests your understanding of particle theory and electron behavior in different materials. For all questions, remember to show you're working clearly, include appropriate units where relevant, and check your answers make physical sense. Write your answers now before looking at the solutions on the next slide. Physics principles of thermal conduction power our modern world. Let's see how today's concepts apply in practice. In technology, heat sinks in computers use aluminum fins to conduct heat away from processors, preventing overheating and maintaining optimal performance. The high thermal conductivity of aluminum enables efficient heat removal from electronic components. In construction, double-glazed windows trap insulating air between glass panes, reducing heat transfer and improving energy efficiency in buildings. The air acts as a thermal insulator, preventing heat loss in winter and heat gain in summer. In cooking, copper-bottom pans distribute heat evenly across the cooking surface because copper's excellent thermal conductivity eliminates hot spots and ensures uniform temperature. These applications demonstrate why understanding thermal properties matters. Career-wise, this knowledge leads to many professions. Thermal engineering designs cooling systems, materials, science develops new insulators and conductors, and energy efficiency specialists optimize building performance. The concepts you learn today become tomorrow's innovations in sustainable technology. Let's review the solutions to build your confidence. For question 1, the answer is, Good thermal conductors include copper, aluminum, and steel, all metals with free electrons. Thermal insulators include wood, plastic, and air, materials with tightly bound electrons or low particle density. This demonstrates the fundamental difference between conductors and insulators. For question 2, we design an experiment using identical rods of different materials, attach small wax pieces at equal intervals, heat one end of all rods simultaneously, time how long each wax piece takes to melt, then compare results to rank thermal conductivity. This method ensures fair testing with controlled variables. For question 3, metals are better thermal conductors because they contain free electrons that can move throughout the material, rapidly transferring kinetic energy between atoms. Non-metals have electrons tightly bound to specific atoms, preventing efficient energy transfer. Now, exam success tips. First, always show you're working even if unsure. Partial credit rewards correct method. Second, include units in every calculation step. Omitting units loses marks. Third, understand command words. Describe means state observable features. Explain means give scientific reasons. Fourth, draw clear diagrams with labels when describing experimental apparatus. Let's summarize today's lesson on good and bad thermal conductors. The key points to remember are, first, thermal conduction involves heat transfer through direct particle contact, where kinetic energy moves from high-energy particles to low-energy particles within the same material. This process requires no bulk movement of the material itself. Second, thermal conductors, particularly metals, contain free electrons that can move throughout the material, enabling rapid heat transfer. Examples include copper, aluminum, and steel, which are widely used in applications requiring efficient heat distribution. Third, thermal insulators are typically non-metals that resist heat transfer effectively because their electrons are tightly bound to specific atoms, preventing efficient energy transfer. Examples include wood, plastic, and air. For further study, review experimental procedures and safety requirements for thermal conductivity tests. Practice comparing material properties using quantitative data and graphs. Prepare for the next lesson on convection and radiation, which covers the other two methods of heat transfer. These three mechanisms, conduction, convection, and radiation, complete the thermal physics foundation essential for Cambridge IGCSE physics success.